Hi everyone, my name is Song In-hong, PhD student in Compilers and Systems Lab. I will introduce my research titled Compile Time QS Scheme for Deep Learning Inferences. Recent advancements have driven the wide adoption of deep learning across numerous application fields. Consequently, services generate a vast number of inference requests that are processed on shared accelerator. While resource sharing or request batching improves system throughput, it increases the latency of individual requests. Depending on the service type, inference requests should be completed within the target latency. Violating this latency target results in poor service quality or, in extreme cases, failure. Modern DL accelerators have adopted throughput-oriented architecture, often neglecting time constraints. This complicates the provision of QS for DL services. Previous QS scheduling approaches ensure QS by conservative sharing, such as temporal sharing, spatial sharing based on hardware partitioning, or padding-based collocation. Those approaches prioritize the QS request and allow non-QS kernel co-execution only if it doesn't interfere with the performance of the QS request. In temporal sharing, when a new QS request arrives, the scheduler resets the running non-QS kernel and dedicates time slots to the QS request. Those conservative sharing approaches are stable to provide QS, but can't achieve high performance due to low resource utilization. To achieve high performance, a scheduler should collocate both QS kernels and non-QS kernels. However, due to resource contention, scheduler should decide collocation per every kernel execution. The scheduling includes 4 steps: latency prediction, QS headroom evaluation, collocation decision, and QS headroom update with actual latency. The scheduling overhead is negligible for scheduled long-running kernels such as in HPC workload. However, the scheduling overhead becomes problematic among DL inferences. DL inferences typically consist of a sequence of short-running kernels, making it impossible to hide scheduling overhead, even a millisecond scale. Our key idea is to find the QS plan, specifically a kernel slicing plan, to ensure given QS target at compile time. When requests arrive, apply the targeted plan T1 here to apply the plan to the non-QS model runner, and then leave scheduling and execution to the native system. I will continue to describe the details in the slide after the backgrounds. In the background, I will briefly explain the fundamentals of kernel execution on commodity GPUs under multi-process service enabled. The background would help answer the following question: how could pre-sliced kernels perform as QS at runtime? In GPU programming, kernel is a function which is executed in single instruction multi-thread manner. The kernels will be launched in the host process. Because those APIs are asynchronous APIs, if a read process A scheduled first, it launches all its kernels immediately. The launched kernels are queued in CUDA stream. The head kernel K1 will be delivered through device driver to execution engine queue on GPU. When the kernel is scheduled in a concurrent scheduler, it will be decomposed into thread blocks and sent to thread block schedulers. The hardware implemented thread block scheduler dispatches a thread block to one of available streaming multiprocessors, SMs. A single SM executes multiple thread blocks concurrently. The maximum number of thread blocks are limited by the resource usage of the corner. This limit is called block occupancy. A GPU can execute up to block occupancy multiplied by number of SMs concurrently. It refers to one wave. After all thread blocks of K1 have been dispatched into SMs, it's returned to send K2. But K2 is blocked by implicit synchronization policy in CUDA stream. Meanwhile, if a new process B has been scheduled, the process launches its kernels into another CUDA stream. K3 will be sent to thread block scheduler as the same procedure as I described. When several thread blocks of K1 have been completed, thread block schedulers dispatches thread block of K3. This is enabled under MPS's leftover scheduling policy. According to the procedure, kernels of the following process interrupts kernel execution of the leader process. Under this mechanism, we found that splitting kernel execution of low priority tasks has a similar effect to preemption. The left figure illustrates execution of a co-scheduled process P1 and P2. P1 arrives first and occupies all SMs. P2 should wait until any SM becomes available. If P1's kernel has split into two kernels like the right figure, the waiting time of P2 will be reduced. If we find a suitable kernel slicing plan, QS can be ensured. To search for optimal slicing plans, we set the hierarchical research objectives. First, find a plan that must ensure the specified latency target. Second, find the most efficient slicing plan to maximize system's performance. Lastly, the search time should be in reasonable time. The objectives remain in two challenges: vast search space and high QS validation cost. Typically, inference tasks consist of a sequence of tens to thousands of kernel launches, and each kernel has 1 to thousands thread blocks. Potential search space becomes a multiplication of all three dimensions. Additionally, QS validation tests on a candidate plan requires a high cost. As in real-world use cases, requests do not always arrive at the same time slot. To achieve reliable results, it requires numerous iterations of measuring latency on a real device. To address the problem, we propose QSLicer that integrates heuristic search algorithm and latency estimation model. QSLicer searches under three policies for bounding search space to efficient and predictable. To reliable and lightweight testing, our latency estimation model provides conservative and robustness. Our model estimates every sliding scenario and returns a specified percentile latency. The estimation is based on profiling. To avoid iterative profiling, we designed a robust model to take profile of the original kernels and slicing plan only. To define the heuristic policies, we analyze kernel slicing, focus on three perspectives: efficacy, efficiency, and predictability. When applying kernel slicing on a task, another co-located task would be completed faster. We define this extinct as efficacy. To fully understand efficacy, we need to examine efficiency first. Suppose that slicing the kernel into S slices in near uniform distribution, Slicing achieves maximum efficiency when the total duration of slices equals the original corner's duration. In this ideal case, the slice's duration is the corner's duration divided by s. On the other hand, the least efficiency can be achieved when no reduction in the duration of slices. Unlike simple examples, calculating the duration of a slice is way more complicated in the real world. Because of complex factors such as thread parallelism, data instruction locality, and sub-memory systems affect the duration. So, therefore, we represent the duration in the range. If we maximize QoS efficacy without considering efficiency error, we just slice the corner into as many as each thread blocks, then make each slice occupy the minimum resources. To avoid that, we refine efficacy as the gain with consideration of efficiency. Then the gain can be represented as the range from 0 to duration of corner subtracted by duration of slice. Since we define the duration and the gain as ranges, the co-located latency is still unpredictable. Specifically, execution time of co-located thread block is not uniform. After some co-located thread blocks are completed, it is impossible to predict how many instructions remain in others. To make space predictable, we bound the search space to the most effective and efficient space. We search this space first with our estimation model, and then we enlarge the space with a QoS validation on a real device if necessary. To bound the most efficient search space, efficient thread block partitioning is essential, but I have limited time, let me skip the details. In short, QSlicer partitions thread blocks into slices containing multiples of the number of SMs to reduce tail latency. If there is a remainder, the final slice executes those additionally. And then finally, here is the overview of QSlicer. QSlicer takes two lists of corner information and latency target T here as input. Each element in the list contains duration of corner and wave. This profiling data is retained during profiling-based compilation. QSlicer uses two lists, slicing plan and blank list, for non-QoS task only. An element of slicing plan indicates number of slice will be applied to this corner. Then which is initialized as 1. True false in blank list represents the corner can be sliced more or not. QSlicer set true to the corner which has less than 2 waves, because if slice this corner, it will become partial wave corner. If it finds a solution to meet the target, it returns a slicing plan that indicates how many thread blocks will be launched per each slice of each corner. The partitioning method is fixed up. QSlicer can represent the solution in one-dimensional array. Deep dive into QSlicer's search algorithm, then QSlicer performs linear search in slicing the largest wave first policy. Note that we implemented heuristic cost function to skip the estimation cost. If a slice contains less than 2 waves after slicing step, QSSlicer excludes the slice from the candidate. QSSlicer terminates the search either solution found or no more candidates. When QSSlicer terminates the search without finding solution, it switches search mode to aggressive mode. In this mode, our estimation model can't guarantee conservative anymore. QSSlicer continues to search using adjusted target with real latency, which is measured on real device. To ensure adjusted target positive, we multiply this ratio. We defined the error function as shown here. Negative error means this plan can't meet QoS. Otherwise, positive error represents the difference from target while ensuring QoS. If the real latency is less than positive 1% of error, QSSlicer accepts the solution to remain reasonable search time. For evaluation, we select 5 DNN models with different characteristics, relative execution time, and proportion of slicing candidates. We set 3 QoS load levels motivated by the ISB benchmark, low, medium, and high load. For thorough evaluation, we enumerate all possible combinations in 75 workloads. To evaluate QoS satisfaction, we use good pull rate, which is number of QoS requests completed within each target over number of total issued QoS requests. Among 75 workloads, QSSlicer successfully finds all solutions while every solution satisfies targeted P99. To evaluate throughput improvement, we compare this QSSlicer with the baselines NVIDIA MPS and RIF. MPS shows near optimal throughput, but it can't ensure QoS. RIF is a SOTA scheduler while providing reset-based preemption and dynamic kernel padding. For overall throughput, QSSlicer shows equivalent throughput to MPS in 30 out of 75 workloads. QSSlicer improves non-QoS throughput compared to RIF by 20.2%, excluding the starvation cases under RIF. The right figure illustrates an example of QoS BERT and high load scenarios. For 4 workload, non-QoS of BERT, Conformer, NERV, and ResNet 50, MPS fails to meet QoS. On RIF, non-QoS requests never finished in NERV workload. It happens due to RIF repeatedly reset the long-running NERV kernel. Our scheme requires code transformation. It introduces only minimum overhead up to 30 microseconds. Additional kernel launches are hidden by GPU computation, and block ID remapping within device code rarely increases research usage, but it barely limits block occupancy. Here is the conclusion. We propose a compile time QoS scheme that providing predetermined kernel slicing plans at compile time. And we developed QSSlicer, which integrates heuristic search algorithm with a robust latency estimation model. And we also developed code transformation that parameterize kernel slicing. Our experimental result shows 20.2% of performance improvement compared to SOTA scheduling. Thank you for listening. If you have any questions, feel free to contact me via this email. Thank you.